Okay, good afternoon, everyone. Welcome to the second installment of the August mini school. I only need to introduce briefly the speaker, Omid Hassasfar, here in Stellenbosch. Actually, he's sitting next to me. Yeah, and Omid, everybody knows the rule of the game. Yeah, if you have questions, please post them in the Q&A, and at the end of the webinar, we can give you the opportunity to ask the question in person if you so desire. Yeah, and Omid, if you want to start sharing your screen, you're most than welcome, and then you can start. Yeah, and we are very much looking forward to see what PennyLane has to say. Yeah, today.
I think you need to mute yourself. Okay, thank you very much, Francesco, for the introduction. Okay, let me share my screen first. Okay, can you see my screen now? Okay. First things first, let me quickly, first of all, share the GitHub link to everyone that wants to follow what we are doing here. This is the GitHub link specifically for this mini school. And I mentioned in the first session, but let me quickly mention it again. In the GitHub, you have one Jupyter notebook that you can click on it, and then you should be able to open it in your Colab, Google Colab. And when you open in your Google Colab, you don't need to be worried about your environment, your IDE, it's VS Code or Jupyter Notebook or this kind of thing. So we don't need to spend time on those things. You just need to run your code. That was the first things. I hope everyone have access to the link. The other things is, last session I introduced the previous NITheCS schools on quantum computing that you have access to the recording sessions. I added the first session, actually the playlist of this mini school here, so you can check the number 6, which is the playlist of this mini school as well, along with the other resources that you have. And okay, that's the first things that I wanted to mention. For those of you who want to learn more, I also put this resources mind map that you can explore more different resources, including many interactive courses and I don't know, different quantum games, lots of things. Okay, installation. We did it last session. Installation and then checking the version, everything here. And one of the questions that I got the last session was the connection between PennyLane when you are working in PennyLane and you want to use the other hardware devices. Yeah, you can. And the answer was yes, but I didn't show you how to have access to this. If you go to this page that I provided here, you can see that there are some using PennyLane on the cloud. You can check this web page to see how you can connect your PennyLane code to Amazon Braket or other provider like IonQ, Circ, and then you can browse all devices. Then you can see how can you use all those real quantum hardware to test your code. Okay, that's the link that you need, then you can explore. And also, if you are interested to know about the real quantum hardware, these are the lists that you can have access and then see different features that they have, number of qubits, fidelity, and I don't know, connectivity, and lots of things. Okay, I didn't mention this, but in PennyLane, apparently, we don't have, maybe I need to a little, is it better now? Okay. in PennyLane, actually, I couldn't find the built-in function to show you the state of your vector in the Dirac-Ket notation. So I provided this function, which is not built-in in PennyLane, but so we have this line of code to use basically if you have your state and you want to see the state in your bracket notation, you can use print state ket, but you need to, of course, run this cell. And also, I couldn't find any histogram plotting in the PennyLane, so I wrote this function as well. So these are not built-in function in PennyLane, but you have it here, then you can use it whenever you want. Okay. Let me, maybe you can do it with me. Let me just run it here to see if everything works. It should work, actually. I also checked, it's always better to check the version of different packages that you are working with. Okay. Okay. The next things that I want to mention is, these are the resources that I mentioned. Okay, we basically explored this coder size, and these are the resources that I'm using for this specific mini school. And I think I mentioned about the codebook of PennyLane that I encourage you to sign up and register with your email address, and they try to check this learning path. It takes a few, probably months or even 1 year to finish all those materials because it's very comprehensive. You can see a lot of materials there, but I'm specifically using these two modules, that foundations of quantum computing and also PennyLane fundamentals. Okay. The other thing that I mentioned last session was kind of the table for your built-in gate, or which is unitary operator or unitary matrix that you have here. You can check those gates here. Also, I added this one. This is, if you want to quickly check this measurement cheat sheet as well. So in PennyLane, you have basically, based on this table, you have 4 different types of measurement that I want to explore quickly today. Maybe not this one. This one is for maybe next session, because I need to explain a little about expectation value. What is the expectation value is in quantum mechanics and quantum computing, maybe next session, but you have it here. Okay. This is, I selected some of those coder size. So this is just a simple circuit that I use. Let me quickly review what we did. Actually, we have our simulator, which is our device, and we have our quantum circuit as a Python function. And then we have this Q node to kind of connect this quantum function to the simulator. So here you have some standard gates that I mentioned above, that you have the link, then you can have access to all the matrix form or the of this unitary matrix or gates. And here I just try to play around with these different gates and single qubit gates, 2 qubit gates, and then try to see if we run this, we in the return function, in the return part, we can have different things. Okay, here I use probability, but we can have state, we can have probability, we can have counts, we can have samples. And here I use probability because I was interested to the probability of the different state that I have. So if you run this circuit, and because it's parametric circuit, so you have 3 parameters. When you have parameter, you need to specify your parameter here, and then when you are calling the function, you need to mention, okay, what are those parameters are. So here is 0.1, 0.2, and 0.3. I chose this. Okay. Okay, this is the probability, and which is a NumPy array. And if you are interested to see this NumPy array in a very nice visual, that you can see in your textbook, you can use I use this SymPy matrix form, which gives you a nice matrix version of your NumPy array. So this is not related to quantum computing, but if you want to see your exact vectors or matrix, you can use this SymPy matrix form to have this one. Okay. And then I just investigated the probabilities of this, and then and that's a quick nasty check to see if your probabilities sum to 1 or not. If you do this, if you use just a standard sum function in Python and your probability was 0.999, because if you add all the probabilities, it should adds up to 1. But if it's not, maybe you need to use a round function to check that, okay, if you round it to 7 decimal, it is 1, which is basically acceptable. And then you can draw your circuit. I use this barrier to kind of visually separate. Yeah. And I also recommend to use style as a PennyLane, which is much nicer if you want to publish somewhere or write a blog post or whatever. This is much nicer. Okay. So you have a bunch of built-in gates, single qubit gate or 2 qubit gates or 3 qubit, multi-qubit gates. But if you have a specific matrix and then you want to use it as a gate, what should you do? You should use this function, qubit unitary. So this is your matrix, which is it should be, of course, unitary matrix, 1, 1, 1, minus 1. And then with this function, qubit unitary, you can basically define your custom gate, which is if this is not part of the standard built-in gate. So that's also one important thing that you need to know about custom gate in PennyLane. And if you are interested, you can check if the U is unitary or not. This is U. And then I use this symbol function. So unitary means U dagger should be equal to identity. So this is the conjugate and this is a transpose. So U dagger means conjugate transpose. So you can use conjugate transpose to, and then multiply them to get your UU dagger, which is this one. And then again, I rounded to like 10 decimal something, because sometimes you have these to the -17, to the power of -17, which is basically 0. So yeah, this is correct. And actually we knew that because it was Hadamard gate. Okay, I define it as a matrix, but you have it as a built-in gate. But I just wanted to check if you want to define your custom gate. Okay. And as I mentioned that I defined this function to show you how, if you simulate your quantum circuit and then you have your state as a return, PennyLane didn't give you a nice bracket output. And if you wanted, I wrote that function. So if you want to see your state vector as a bracket, you can use this function that I wrote, print state kit. So this is of course your result, the state function of the state of your quantum circuit. But and if you are curious to see this is the vector that you have. But if you are interested to see something like this, which is sometimes you prefer, you can use this function that I already wrote. So here we have 3 qubits, and when we specify here the number of qubits, wires or qubits. So here we have 3 qubits, and when you have 3 qubits, 2 to the power of n, or 2 to the power of 3 here, you have 8 different states. Then you can see 1, 2, 3, 4, 5, 6, 7, 8 different states, each of which has its complex amplitude. Okay, and okay, a little play around with this to show you how to basically see this. This is a uniform superposition, so you can see the probability of each of them are equal. Okay, and maybe it's also good to see the famous GHZ state. If you are curious, you can check this link to learn more about GHZ state. But basically here, by default, you know that in PennyLane and also in many other packages, we start with 0, 0, 0. All the qubits initialize by 0. Then here we apply the Hadamard gate to the first qubit, and then CNAT gate to the 0, 1, and another CNAT gate to the 1, 2. So you can see, you can follow the steps here. This is the effect of the H on this first qubit, which is this one. And then I didn't mention a lot about tensor product, but maybe I should. But if you check the one of these, for example, this one, if you check the, let me just quickly show you where should you check, because one of the goal of the schools is to give you the material to check, because we cannot definitely cover everything here. But if you check circuit with many qubits and multi-qubit systems, then you can find a lot of things about tensor product. And so when you have more than one qubit, which is usually the case, we don't want to only work with one single qubit. So this is the standard and very simple definition of the tensor product, which we use when we want to describe the system which has more than one qubit. And as you can see here, the rule is very simple. This is your first vector, this is your second vector, and then you see that how can you create a tensor product. And this is the state of 2 qubits. And of course, when you have tensor product for the state, you have tensor product for your unitary operation, which defined as you can see here. So you need tensor product to define your state and your unitary matrix. And when you define this, so when we write something like, for example, let me just show you. When we write something like 0, 0 means 0 tensor 0. When we write something like 0, 1, it means 0 tensor 1. So we don't usually write something like this because it's lengthy and it's not nice. But at the beginning, when you are learning, it's maybe good to just write everything and put tensor product here. But when we don't put tensor product, it implicitly means 0 tensor 0. Okay, just keep in mind that's also another things. Okay, let's move back to the. So we don't write tensor product explicitly, but 0, 0, 0 means 0 tensor 0 tensor 0. Okay, applying CNOT on the 0, 1, and then you get your psi to state. And the effect of CNOT is you have control, you have target. And when your control is 1, your target, you apply the X gate to the target. And we apply 2 CNOT gate to our qubit here. And then you can see here, 0, 0, 0 is still 0, 0, 0, but 1, 0, 0 is 1, 1, 0. So this 0 becomes 1 because of CNOT. And also here, you can see 0, 0, 0, 0, 0, 0. Because the control is 0, we don't change the target. But here we need to change the target because the control is 1. And then at the end of the day, you have something which is called GHZ, which is maximally entangled state between 3 qubits. Okay, because we have different degrees of entanglement. All the entanglement is not maximal, but this one and the Bell state that I didn't mention is maximally entangled state. And that's the method that we use. That's the code that we use to run it. Okay, simple. In PennyLane, you can just need to, okay, these are always the same. And you need to define your device, and then you can, the Q node, decorator, and function. So Hadamard, CNOT, CNOT, and here you specify your control and targets. Okay. Here I use like a compact version of the return. In the return, you have both probability and the state. And then you can run the circuit like this. So the first argument is your probability, the second is your state. And when you check the state and probability, your state vector is something similar to this. It's 3 qubits, 2 to the power of 3. It has 8 the possibility, and also the probability is 0.1, 0.5. And if you add this probability, of course, it should be 1. What else? Oh, okay, as I mentioned, this is the function that I wrote, for example. Now we need to, it's better to see, we have, of course, we have 8 different possibilities, but the amplitude of 6 of those 8 possibilities are 0. So when you write your state in the bracket notation, you only have 0, 0, 0, and 1, 1, 1 with these probability amplitude, which is in general a complex number. Okay, and then you can, of course, have the histogram plots, which is this one. Okay, we are doing, we are running our circuit in a ideal simulator. If I don't have this to show you, but if this is a real device, you will see some small probabilities here as well, which kind of show you about the kind of showing the noise. But here is ideal situation. So those probabilities completely 0, and then we have 50% state 0, 0, 0, and 50% 1, 1, 1. Okay. This is another example, but you have the code, you can play around with it, which is, yeah, I chose it from coder size A11. Okay, I don't see any. Yeah, for example, here you have all those. This is 4. This is for 4, I think. Yeah, this is for 4 qubits, and for 4 qubit you have 16 different possibilities, and these are your states, and these are your probabilities. And you see, because this is, we call it uniform superposition, and then you have this uniform superposition with equal probability. Okay, I mentioned about the different measurements, and then in PennyLane. So if you check here, I think I just show you, but let me just quickly open it again. Yeah, you have PennyLane measurement cheat sheet. Let me silent. Oh, no. Yeah, you have 1, 2, 3. Different measurement. Is everything okay in from your online audience? Can you just, okay, nobody complained. Okay, okay, I think, okay, thank you so much. Just wanted to check that everything is okay. So so sample count and probes, let's just quickly check all of them, and then we can jump to the one of the most famous protocol, which is quantum teleportation. This is the last thing that I want to mention today after the just checking this measurement. Okay, measurement, these are the circuit is not important here because this is just a very simple circuit, but different options that you have. The first option, you have the QML sample that it gives you lots of zeros and 1, depends on your circuit. So this is a Hadamard, this is a uniform superposition for 1 qubit. So 50% 1, 50% 0, and then you can check that you have a bunch of 1 and bunch of zeros. Okay. The other things is counts. Okay, counts exactly give you the, here we need to increase the number of shots to give you something more sensible. So I use 2 qubits here, and again, this is the uniform superposition. So here you have 0, 0, 0, 1, 1, 0, and 1, 1, 4 different possibilities if you have 2 qubits. And then corresponding to these counts, you can define probabilities. So these are in the probabilities, so QML probability props, you don't have, you don't know what is exactly this one, but if you compare these two results, counts and props, probably you can guess that this is 0.25 is correspond to state 0, 0, and 0.25 correspond to 0, 1. Again, the third one correspond to this, and the last one is correspond to this one. And of course, the state we already saw in a lot of examples. This is not measurement, but if you are interested to check your state, you can find it here as a vector. Keep in mind, so far, when we talk about state, we are talking about vector. But there are another representation of quantum state in quantum information, which is called density matrix. And at the end of the quantum teleportation, I just want to briefly touch it. So just keep in mind, for representing your quantum state, you have two different options. You can use the state vector, which is a vector, something similar to this, or you can have matrix. So why we need matrix? What is density matrix? That's another story, but it's good to know that sometimes we have to even sometimes to check the system state with matrix, not just vector. Okay. Okay, the last things that I want to discuss today is one of the most famous quantum protocol, not algorithm, maybe protocol is better, which is called quantum teleportation. Okay. I'm using this tutorial here, which is very nice. And then also, if you are interested, you can check this quantum.country. I really recommend you to check this website, which is very nice, written by the famous guy, Michael Nelson. And it kind of, it's like a journey that you are, when you are learning, this is also the definition of teleportation. And it asks you some question and helps you to remember all the concept that you learn. So that's also very nice. I don't want to talk about this. I only want to talk about this tutorial. Okay, quantum teleportation. But for quantum teleportation, we need to know some basic thing that in PennyLane that I didn't mention yet. One of them is state preparation, but it's just one single line of code. State preparation, as I mentioned, by default, all your states in PennyLane and most of the packages of software that I know are initialized in 0, cat 0. So, but sometimes you want to have different psi, not just 0. So you can use state prep function to basically prepare your state. So how should we use it? This is just, again, your simulator, your decorator, and then defining your function. By this line, you can define your state, which is here, for example, I think 2-qubit states. And of course, your state should be normalized. You cannot just define any vector as a valid quantum vector. You should be normalized. So, and then you can read this part, which is the PennyLane fundamental quantum operations part. I don't want to teach all of them, but state preparation, that's something that we need for this algorithm. The other things that we need that I didn't mention is QML condition, okay, which applies a quantum operation only if the given classical measurement condition is satisfied. What does this mean exactly? It means that you measure your quantum state and based on the quantum states, or sometimes they call it mid-circuit qubit measurement. I will show you in the here. Yeah, for example, here you measure your quantum state, and based on this measurement, you apply a quantum gate on the other qubits, for example. So it's like conditional. Okay. So this I mentioned about quantum state preparation and the conditional, then you can read here. So first step, we need to define our simulator and the qubits. Here we have 3 qubits. S, which is our source qubit that we want to teleport. So here we are talking about quantum teleportation. We don't want to teleport human or animal or object. We want to teleport quantum state. But this is also very interesting and important. So we want to teleport quantum state. Keep in mind. So this S is the quantum state that we want to teleport, and A stands for Alice and B stands for Bob. Okay, we define our simulator here. The next step is your state preparation. We want to, as I mentioned, you can prepare arbitrary state here with this state QML state preparation, and you need to specify which wire or which qubit, which is here, I mentioned S, the source qubit that I want to teleport. Okay. Maybe, okay, let me just close this extra stuff here. Okay. I encourage you to read this blog about quantum teleportation. I just want to mention the important things that we have here. Okay, these are the steps that we need to consider. State preparation that I mentioned, okay, this is just a random state, alpha, ket 0 plus beta, ket 1 that I want to teleport. That's the second step is, which is very important. We call it E-bit or entangled bit between Alice and Bob. So that's the second step here. Entangled qubit create an EPR. We call it EPR or Bell state. So, and that is very, very common to know that you apply Hadamard and then you apply CNOT. Here, because we started with the initial 0, 0 and applying one Hadamard and then applying one CNOT, we get one of the psi plus, I guess. We have psi plus, psi minus, phi plus, phi minus, 4 different Bell states, which is very common and famous. Here, okay, we created, because we started from 0, 0, we created psi plus. You can read about Bell state on those materials that I mentioned. Okay, that is the second step. The third step is change of basis. Okay, now the A or Alice converts her 2 qubits from Bell states to the computational state. So basically, yeah, you have your circuit here. That was our first step. I put this barrier to mention, okay, that's your first step. That's your second step. Second steps. Here, they created the entangled pair. So Alice has its qubit that wants to transfer to Bob, which is here, and necessarily is they are not close to each other. Of course, when they want to share this, let's say, entangled state, yeah, they need to be close to each other to kind of create this shared maximally entangled state. But after that, Bob can go somewhere else, Alice can go somewhere else, and they have their shared entangled state. Okay, the third step is here. Alice perform a CNOT between her qubit S source that wants to teleport, and the other qubit that she has, and the Hadamard gate on the source qubit. So that's the third step. And I mention it here. So now you have C0 between source and Alice, and then Hadamard on the source qubit that we want to teleport. Keep in mind, we want to teleport S. Okay. Here we have two different methods, the traditional standard teleportation, which we use the conditional gate, and the other method that I will mention in a couple of minutes. Okay, let's first consider the standard teleportation. And now we need to measure and okay, if you want to just check it here, measurement. Here, that's very important things. Alice measures her 2 qubits. So first of all, we have 2 measurements. And that is very important. When you measure this qubit here, basically, you don't have this psi, okay? Because this psi is alpha 0, beta 1. But when you measure it, it's either in the state 0 or the state 1. This psi will collapse to either state 0 or state 1. So basically, you don't have this anymore, okay? Keep in mind, when you want to teleport, you have to measure this. And when you measure this, basically, you don't have this source qubit in the Alice part. So you only are teleporting to the ball. So 2 measurement, first measurement here and then measurement here. So Alice basically measures her 2 qubits. Then tell Bobs. Okay, what does it mean tell Bobs? Alice can pick up the phone and call Bob that, okay, you need to do these operations. Okay, here we have 4 different possibilities that I'm going to tell you. Okay, how to convert his qubit to obtain the desired state. Here, if both, I didn't mention I had a table, but sorry, I forgot. Maybe after Minischool, I will put the table or something here, but there are 4 different possibilities. If both states are 0, when Alice measure S and A, she just called Bob and said, do nothing. Just the state you have is psi that I wanted to teleport. And when the S is 1 and the A is 0, you can see here, the Bob needs to perform Z. When this state is 0 and this state is 1, you can see here the Bob needs to perform X. And when both states, when Alice measure S and A, when both states are 1, Bob needs to perform first X and then Z. So Alice call Bob and tell him to perform either of these 4 different possibilities. Okay, we basically, and that's a good exercise for you to play around with this. I don't want to say matrix vector multiplication. It's better to just write it in the bracket notation, okay? You have all the derivation here, so we don't have time to derive all the steps, but I highly recommend. So you start with these states, and then I think, yeah, you start with these states. This is the source side that we want to teleport. This is the state 0 for Alice and Bob. And then step by step, when you apply, for example, first Hadamard C0, you get this. And then after applying the second part, for example, here, you get this. You have all these steps here. I highly recommend you to go through it. If I want to just drive it, it takes maybe 30 minutes or maybe more. But but you can do it with pen and paper. You don't need anything else. In some stage, you need to just factor some of these kits, and at the end you will have something. I think, yeah, that's the last part. At the end you have this. You have 1, 2, 3, 4 terms. If you apply step by step, Hadamard, CNOT, CNOT, Hadamard, and then you get this part. 0, 0, 1, 0, 1, 1, 0, 1, 1. And that's the part that I mentioned. You have 4 different possibilities. If Alice measures her qubits and gets 0, 0, she is sure, she's sure that the Bob has exactly the state psi that we wanted to teleport. If it's 0, 1, I think it's the, yeah, Bob needs to perform X, here perform Z, and here perform X, then Z. That's the general story of after driving those steps, which I encourage you to do that after this session. Okay, here let's explain everything about what you need to perform. And in PennyLane, we do this with after measurement. So this is the measuring S and measuring A always, and then it's like a conditional operation based on the measurement. If the measurement is 1, you can apply X and Z to the Bob qubit that I show you here. Okay, let's try and see what we have. This is just a random general quantum state that we want to teleport. Okay, 0. It's 1 over square root 2 plus 0.3i, and I mentioned the first session that your state vector can have complex coefficient as well, and 0.4 minus 0.5i. Okay, this is just a random state that we want to teleport. Okay, so we want to teleport here to Bob. If you are just interested, I just here quickly check if this is a valid quantum state, which is. Okay, here is important. I don't want to dive into the density matrix and the fidelity, but we use density matrix, I mentioned, to show our quantum state in some specific situation. One of them is here. Why we need this? Okay, this is the function that I wrote teleport and gate B state. So we wrote this part: state preparation, entangled qubit, basis rotation, measure and update separately in the above cells. And for the return, because I'm only interested to the Bob's final state. Okay, and these are maximally entangled state. When you have entangled state, you cannot only measure the one part. So now we have to use the density matrix concept. So we cannot just say, you can see here, I commented this. So you cannot say state, measure the state, or return me the state. We need density matrix. Okay, again, just the basic definition. Density matrix is another representation of your quantum state that you need to use in some specific situation, including here. So if you if you apply all these gates and measurements and then write this function, the Bob's density matrix part, we usually denote density matrix with rho, but rho B means the density matrix which belongs to B, Bob. And then you can check this at Bob state. Okay, this is density, and if we use SymPy to show it to you, this is 2 by 2 matrix. This is not a vector. And what was our state? Our state was here. That was the state that I wanted to teleport. Okay, now my state is vector, and my final state that Bob has is the density matrix. So I have to use a trick here, which is a built-in function. So I have to change the state of this. I have to change this vector to matrix. I think I mentioned here, where can you find? Okay, there is in the codebook, there is one module that explains about, I think, yeah, if you check this here, it explains all about density matrix. Okay, I put the link here. I encourage you to check this part. How should you define density matrix? What does it mean? And then all the what is pure state, what is mixed state. So I don't want to talk about this, but for this school, you just need to know that if you have entangled state, you want to measure in one part, you need to use the density matrix concept. So here I define my state, but this is vector. With the built-in function in PennyLane, I changed my vector to density matrix, which is this one. And then you can just see this is, let me just, yeah. You can basically see this state density matrix that we teleported to Bob is basically exactly the same as what we define here, what we define here as a Alice S qubit that we wanted to teleport. That's one method that we can kind of prove that, okay, this state is exactly the same state that we want to teleport. Okay, either you can check this and say, okay, it seems okay, but if you want to do it systematically, you can use another function, which is called QML math fidelity. Okay, and what is fidelity? Fidelity wants to just check both state and tell me that these states are the same or not. Another module is here, so you can learn a lot about these in the PennyLane codebook. So it basically wants to show you the similarity between two quantum states. Okay, we have two quantum states, Alice source state and the what Bob measured. And now we want to compare this. Either we can just print the density matrix and check, okay, this is very similar, or we can systematically check with the concept of fidelity. So then when you check it, where is that? Okay, it's 0.999. Probably if I use the round function here, it will round up to 1. Okay, I know there are lots of concepts here, but the good thing is you need to just open this notebook and you have lots of links that you can spend a lot of time to learn and master those concepts. Last things for today is the fur measurement. So there is, if you just check here, you can read the standard textbook in quantum computing, including the Nielsen and Chuang. And then this is the result of quantum computing, which states that delaying measurement until the end of the quantum computation doesn't affect the probability distribution, which means, so you can delay your, I'd really like to zoom out a little to just show you these two circuits. No, we need to zoom out more. Okay. These two circuits basically are equivalent. So you can see we have psi, we have Hadamard, C0, which we have here. Sorry, I forgot to put the barrier here. And then you have the Hadamard C0, which is here. But what is the difference between these two circuits? In the standard, which is the below one, the standard conventional quantum teleportation, you may always measure 2 qubits and tell Bob to either perform or not X and Z gate. But here, with the defer measurement, you perform this measurement, okay, C0 here, okay, and the CZ here. Basically, it's similar. You can see if this measurement is 1, Alice call Bob to perform Z. And this is also very similar to this. Okay, if this is 1, Bob should perform Z. And this C0 here, if the it's just the dark circle, means that if this state is 1, Bob should perform not, and which is exactly. Sometimes we show with X, and in 2-qubit gate we show with like not. So what we did here, basically, let me zoom in again. We use another method which is equivalent to the standard teleportation. But here, instead of using classical communication, Alice, instead of pick up her phone and call Bob to perform X or Z or not performing both, we need quantum 2-qubit gates directly between Alice and Bob qubits. Okay, so instead of long distance classical communication, we need here short range quantum interaction, because in this part, these 2 qubits now need to interact. Okay, that's also interesting to see. And if you, in PennyLane, it's something automatic. It's interesting that you don't need to, as you can see here, I commented this QML C0 and CZ. You don't need to explicitly write it. If you just choose level device, it is clever enough to put your measurement to the end, and then it can create this circuit automatically for you. And then with this, you can check with some trick that your teleported state is the same or not, which is apparently the same. Okay, let me stop here, and we have a few minutes to check the questions and comments or whatever. Okay, should I mute myself?
Yeah. So are there any questions for Omid? Or comments? Sorry, where's my video? Here we go. There is a comment in the chat, Omid. In which context of problems of real life problems, quantum teleportation can be useful or can be applied for?
Teleportation, I think in both quantum communication and quantum computation, that protocol is very useful. And then I don't, off the top of my head, I don't know in the real life problem, I don't have any specific example at the moment, but it's very, very important in both quantum communication and quantum computation. I need to check. Maybe next session I will answer this question, but that's a very good comment. Thank you. Latte.
I don't see any other question. Are there any raised hands? Let me check. Not at the moment. Omid, it seems you gave the perfect lecture.
Thank you.
Nobody asked questions, and everybody is still there.
Or maybe very difficult.
Now there is something in the chat again. Sorry, let me quickly check. Okay, thank you. Thank you, Eleanor. We will share the thank you with Omid. Yeah. Omid, maybe you want to say quickly what the content of the next session will be.
Okay.
Just as a short preview, so that we make sure that everybody comes back again next week.
Okay, next session, probably we are going to touch a little basic quantum algorithm like Deutsch algorithm. And also, I wanted to also mention about the last measurement that I didn't mention today about the expectation value, how to calculate the expectation value with PennyLane, which is very important. If you are performing any quantum algorithm at the end, you need to do this. These are some, and also I realized I couldn't find anything about the block sphere in PennyLane. I will talk about a little about Blogosphere, how to play around with that as well. These are things that I want to mention. Next session, maybe also I will add something else if I have time.
Okay, excellent, perfect. Then Omid, you receive lots of compliments in the chat. Then I thank you as well for another nice lecture. You shared at the beginning all the links to all the resources, so everybody is happy and welcome to play around. We will upload the video hopefully tomorrow, by tomorrow, yeah. And maybe we put the link to the GitHub also on the website. I have to confess, I haven't checked whether it's already there. Maybe it is. Yeah,
it is.
Okay, wonderful. Then thank you very much, Omid. Thank you very much to all the participants. And we all hope to see you again next week. Yeah, thank you.
Thank you.
Thank you very much. All the best. Bye.